All right. Thank you for coming. It is my pleasure to host today Yossef Zenati. He graduated from the Technion at 2020, I think, and since then he's been a postdoc at Johns Hopkins University. And I always like to tell fun facts about our speakers. And Yossef is the first person that obtained a PhD in physics from the Jewish community. It's a community of Arab-speaking minority that lives in the northern parts of Israel, Syria, and Lebanon. And they're very special, to me at least. And if you want to know more, you can go to Wikipedia or ask Yossef later after his talk. And today he's going to talk about, can you share your slides so I'll know what you're talking about?
Yeah.
I'm kidding. Yeah, so today Yossef is going to talk about white dwarf main sequence star mergers, formation, and outcomes. So without further ado, please take it away.
Yeah, okay. Thank you, Evgeny. Thank you. I'm happy to be here in this nice group, and nice to meet everybody. My main topic or interesting area is theory and simulation, specific in transient or extremely complicated transient as binary stars, type 1a, collapsor or supercollapsor. And recently I'm focusing more in magnetic helicity of neutron stars. So if anyone want to share or talk about it, so just please send me an email and I'm happy. And today I'm going to describe or to present work done with Brian Metzger and Laura and Kenshin about CV system, novae, and I hope it will be clear. So I will start with describe what is novae to just to make sure we are all on the same page with understanding the basic of novae eruptions. Novae, as in general, novae take place in binary stars, where one object is white dwarf and the other is non-degenerate star. The majority is main sequence. We will see in this talk a specific range of mass we need to explain the CV system. And but sometimes could be a subgiant or giant. And the component star transfer material, as you can see from the sketch here. So, so the component star transfer material onto the white dwarf, where it accumulates as the hydrogen-rich layer on the white dwarf surface. And I just, in each slice in the introduction, I will give trying to compare to supernova type 1a. So the main difference between novae and supernovae is that a novae explosion only transfers on the surface of the white dwarf when an abundance of hydrogen is gathered from the component red giant or main sequence. And in contrast, a supernova is the gradient explosion in galaxies, a super brighter event where the white dwarf reach the mass of Chandrasekhar mass and they explode whole the star. And as the accreting material rains down onto the white dwarf, you can see here the white dwarf surface, it's get hotter and denser and higher pressure at the base of the layer of white dwarf until the critical temperature is reached, the thermonuclear runaway, which takes form of a rapid and dramatic increase the rate of C-no cycling reaction. And the thermonuclear runaway injects a bunch of energy into the accreting layer, which buffer expands the binary and is mostly ejected from the white dwarf surface. Another fact, novae is a bright flare or outburst then occur on the surface of white dwarf around 100,000 times than our sun, but it's far away from compared to type 1a, where they release around 10 to 51 erg energy. And as you can see, the high gravity and intense heat on the white dwarf make condition suitable for hydrogen fusion into helium. And when enough hydrogen collects, it explodes, as a fusion reaction, causing a novae. And the gas ejected in the explosion moves outward at 1,000 to 2,000 kilometers per second. And some states on typical novae eruption are that they typically eject somewhere between 10 to minus 7 to 10 to minus 4. In some cases, it could be 10 to minus 3 solar mass into the space or reach the interstellar at few thousand with velocity eject a few thousand kilometers per second. And the kinetic energy of the ejecta therefore tends to be around 10 to 44 to 46 erg, and the novae are about 1,000 times more common than the supernovae type 1a, without, for example, in our galaxy, about 35 novae expected each year in our galaxy and 10 observed. This is the statistical, the recent statistical data about novae. So to begin this scenario, how the novae occurred at the hydrogen-rich skin, as you can see here, will be gradually accreted. We therefore think that all the novae recur, but the back time can vary dramatically depending on the white dwarf masses and accretion rate. Actually, these specific, the mass of the white dwarf and the mass loss could define the mechanism for losing angular momentum of the system, and that's make the CV system, with what I'm going to describe in the next, more complicated than we thought before. So novae may repeated all these scenarios could be repeated on time scale between year to giga year. This is why the cycling is novae. So why actually? Yes.
Okay. Do you prefer questions at the end, or are you okay with being interrupted with questions?
It's okay. Anytime you want to ask.
I think we have actually a couple, but Steve, do you want to go first?
Yeah, just a very basic question. Have any novae been observed outside the galaxy?
I'm not sure exactly if there's a specific slow novae or novae about our galaxy. I will describe someone they thought it's really a slow novae could be out of our galaxy. Yes.
Yeah.
At the end, yes.
I had.
But it's sorry, but I should mention the bright. The novae, it's not enough. We can detect or through the electromagnetic spectrum. So this is make a problem. But the flare is novae. It could be bright enough we can observe. And this is a question of discussion and open question about how to what exactly novae whites could be faint or not. So yeah. Go ahead, Ilya.
So I noticed that you had always hydrogen-rich material accreting onto a carbon-oxygen white dwarf. What about either accretion of hydrogen-rich material onto a helium white dwarf or accretion of helium-rich material onto a carbon-oxygen white dwarf? How different would that look from a normal nova?
Okay. So I will actually we also simulate where we have a low mass white dwarf with a helium, and I will present it. But the quick answering, if the companion is a helium star, so the novae is super faint. This is what this is. But what happened if we have a helium wide dwarf with main sequence? It's also it could be observed as a CV system. And actually, for decay, they thought a low mass of white dwarf coming from helium white dwarf, it could be the optimal mass to explain how these systems lose angular momentum. I will explain specific the camel mechanism in the few slides. So I hope I can answer it full answering in a few slides.
Thank you.
So why is novae actually as over that century plenty of reasons why they study novae, because they are of course so common. They tend to be nearby. I meaning is especially resolved and nearby and bright. I meaning we can study them across the electromagnetic spectrum, and it become clear novae are wonderful laboratories for studying some of the most important processes in stellar astrophysics, like accretion, thermonuclear reaction, mass loss, and even common envelope physics. Novae also occur on accreting white dwarf, especially Ilia, were therefore important for understanding the progenitor of type 1a supernovae. Although in the last decades, popular opinion has largely turned against novae as the progenitor of most type 1a supernovae, but they may still be important in the minority of cases, and they contribute to our understanding of how white dwarfs accrete and grow in mass. So, is there any question in the chat, Evgeny? Can you check, please?
Yeah, just a comment about some observation that was there was some confirmed observational helium nova called V445.
Yeah, exactly. Specific, I'm going to mention this in the last slides about the luminosity of this issue. So, okay. What is the CV system? So actually, it's a component. I was surprised by Brian. He started to describe for me why we should go through this complicated physics to explain a very specific system, and I was surprised how this compact this system. So I will start with the CV, our compact, the interacting binary, in which a white dwarf, the primary, accretes from the low mass, roughly main sequence donor star. The mass transfer and the secular evolution of the CV is driven by angular momentum loses. Sorry. In system where they have long period, orbital period, above 3 hours, the dominant angular momentum lose mechanism is thought to be the magnetic braking, as known in B, due to a star wind from the donor star. In the main distributed magnetic braking evolution for decays, the scenario for the specific the CVs, the magnetic braking stops when the secondary becomes fully convective, and the orbital period close to 3 hours. At this point, the donor detaches from the Roche lobe, and the gravitational radiation becomes the only remaining angular momentum. The angular momentum lose. This is the main mechanism, and the gravitational radiation-driven shrinkage of the orbit ultimately bring the secondary back into contact at period of 2 hours. This specific period time, it's very important because they define exactly the one of the most puzzling problem in CV system, And I continue at which point mass transfer resumes after they back to the orbital period for 2 hours. And the motivation for this scenario is the dearth of the mass transferring CVs in the so-called, it's called the period gap between the orbital period 2 hours and the 3 hours. I just described one properties of the CV system with the time or orbital period, and there's another 2 orbital period problem with the faint system. As I start to say, like there's long orbital and there's short orbital, where the system will continue to evolve towards the shorter orbit period through the loss of angular momentum by gravitational radiation only. So until the donor becomes degenerate at all with orbital period of 1 hour or 80 minutes. So these systems could be called the AM CVs. It's if somebody interested in specific these systems, it could be between 5% to 25% of all the CV systems. So far, I here just put the tree or the zoo of the closed binary and how the CVs connect to the novae with if there's magnetic or not. They describe in different, the only or the main characterized the non-magnetic to the magnetic between CVs and novae is the mechanism of the angular momentum conserving. So I will in the next slides I will describe the main or the fresh or the novel modeling for conserving angular momentum in these systems. But let me just mention the majority of the we believe the majority of the CV's progenitors is a wide dwarf with main sequence, where the main sequence around 0.3 solar mass. But the wide dwarf masses is still puzzle. It's one of the second puzzle of the CV system. We try to answer this here. If I have time, I will show that or present this. So far, there's strong or existed for decades between the observation and the theoretical prediction of the orbital period distribution. So where the location of a minimum period of this CV system. So the space density of the CV system is found to be 10 to 100 times lower than the theoretical prediction. And the minimum CV's orbital is longer than expected. And this is the first actually open question about the CV system is the period gap. As I just focusing on the long period, we start with 2 to 3 hours. This is the majority of the system. And all the population synthesis studies just agree. So there's 3 gaps of this system, but in the theoretical side, what is the minimum of these gap or where they locate, and that affect the mechanism of how they lose the momentum. So the second problem, as you can see here, is the wide dwarf mass problem. So the first measurement of the observed wide dwarf masses have been significantly higher than predicted, with most of them in the range between 0.8 to 1.2 solar mass. That means most of the CV system must be CO wide dwarf. Recent studies shows, like the last 10 years, shows a completely different mass results of it could be. So perhaps this is the most puzzling of the CV's question. So the wide dwarf masses in CVs are systematically larger than those in their progenitor population. The post-common envelope detached binaries and the formation of large number of CVs containing low mass wide dwarf appears to be the generic consequences of CV's model, regardless of the assumption that you take in your observe or your simulation. But they agree the recent studies, the CV system wide dwarf must be lower mass than they thought before. So they still open question, kind of. So here I'm trying. Is there any question in the chat, Evgeny? Please can you check?
No, we're all good.
Okay. Okay, so the common mechanism for losing angular momentum is the consequential angular momentum loss. So I start with in the novae, the thermonuclear outburst that occur on the wide dwarf surface owing the unstable hydrogen burning. And following the thermonuclear runaway, the outer wide dwarf envelope expands to encompass the secondary star, resulting in a physical situation somewhat similar to the common envelope interaction between non-degenerate binary star. So that the previous studies find that an additional sink of angular momentum beyond that due to the magnetic braking and the gravitational wave. This could be one of the issues to conserving angular momentum. So this mechanism assumes enhanced consequential angular momentum losing from the system itself, and the classical non-conservative model for the camel, the consequential angular momentum loss, assumes that the ejecta mass takes away the specific angular momentum of the wide dwarf in order to explain the observed CV population. The new camel mechanism must preferentially act on CVs with lower mass wide dwarf. And you can see here the recent simulation of the camel. Sorry. They present a new stability limit for the mass transfer in the CVs. So we try in our work, we just assume the same assumption where to deal with conserving angular momentum, trying to estimate the ejecta mass and the accreted mass based on our methods. So far, on the other hand, I'm going to just describe briefly how wide dwarf in general they form. So wide dwarf forms through stellar evolution of single star at the current age of the universe. There are several types of wide dwarf composed. As you can see here, there's CO and helium wide dwarf, oxygen and magnesium. And here what you can see is the radius versus mass of the wide dwarf. And there's a new kind of, it's not new, they known as helium CO wide dwarf. We call it the hybrid CO wide dwarf. I will describe how they could form and why it's useful for these novae or type 1A. So as I said, corresponding to the stellar evolution endpoint of the intermediate and the high mass, this could be the single channel of wide dwarf form, CO wide dwarf or oxygen neon wide dwarf. In interacting binaries, each of the stellar component may fill its Roche lobe and may also evolve into a common envelope phase and be stripped of part of its hydrogen helium rich envelope during its evolution on the main sequence or later in the AGB stage or RGB stage. That can give rise to very low mass, as known helium white dwarf. This is the only or the common channel to form a helium white dwarf, as known the VLM, the very low mass of white dwarf. It's below 0.45 solar mass. In particular, white dwarf's mass is lower than this VLM, are typically thought to be the helium white dwarf and forms through specific this interaction channel, as I mentioned. So the evolution and the final outcome actually of the binary evolution strongly depend in the initial condition as a stellar, the initial stellar component and the initial separation. And the complex binary evolution can give rise to this VLM or hybrid white dwarf. The hybrid white dwarf is the same evolution as a helium white dwarf or the binary interaction, but starting with a different initial mass, actually much higher. And when most of the red giant envelope is removed, hydrogen shell burning is quality, and the helium core keeps growing, and the star begins to be contract. And if the helium core is massive, the contraction will eventually trigger helium, and the formation of the CO core to the helium to the CO ratio will be determined by specific details evolution of the helium burning into CO. And the mass loss throw, of course, wins from the envelope. So to summary how the white dwarf could form, in the single evolution, they could give us the higher mass of CO and oxygen neon could be, and the others of the very low mass, it require a binary interaction to get the hybrid and the helium white dwarf. So far, usually for our simulation, I start with 1D or stellar evolution code, the most as known the MESA, and I can produce the white dwarf, hybrid white dwarf, map it to 2D maybe by using SPH just to see if there's interaction between two double white dwarf or white dwarf main sequence, and then relaxation method, with damping the velocities just for few dynamical time scale, and then map it to flash. Flash code is the AMR code. I will describe it in 1 minute. And also solving the nuclear reaction network, and using the pressure particle method, the passive actually, trying to describe all the isotopes we have for post processing network to figure out the light curve and the spectrum for this event. This is usually what I'm using for this kind of simulation. In Flash also we have, we can use a magnetic field or MHD actually, or we can use a viscosity. So, yes, okay. So we explore, in this work, we explore the direct observational signature of the death of the CVs in dynamical mergers. The final outcome of the unstable mass transfer processes is that the tidal disruption of the secondary star, in this case main sequence, resulting in the formation of the massive hydrogen-rich disk around the white dwarf. So for that, we use a 2D axis symmetric cylindrical coordinate on large grid. I mean large, it's significantly large than the orbital size of the CV's binary prior to the emergence, above 10 to a few times 10 to 13 centimeter. So we solve the equation of conserving mass, momentum, energy, and chemical species, and we do not, in this case, simulate the dynamical disruption phase itself. we start our simulation after the disk has formed and focus on the system evolution that occur on longer viscous time scales, over which the geometry will be approximately isomorphically symmetric. And the process of unstable mass transfer culminates the dynamical disruption of the secondary into a massive disk surround the wide dwarf, which subsequently accretes over the arc days at higher super-Eddington rates. This is what also we get in this simulation. So we present in this work 6-7 models with different mass of wide dwarf, different mass of secondary, in this case main sequence, and I try here the helium wide dwarf, the 0.3. I will also trying to give some benefits in this model. Well, the last here you can see the viscous time scale for the initial time of this system for the outer edge of the disk. So what is the disk I talking about? So our simulation, including both hydrodynamics and thermonuclear reaction and alpha viscous following our previous simulation as when the black hole wide dwarf merge, the wide dwarf is tidally disrupted and sharing into accretion disk. This actually, this work done by Papaluzzo and later in Frey and Mosley in the 90s, and they're trying to consider the merge of the wide dwarf black hole as a progenitor of the long GRBs. They explore the dynamical of disk formation during the unstable Rausch-Lobe overflow in circular orbit around the stellar mass black hole. They use SPH simulation with nuclear burning and predict the accretion power expected from the resulting disk. Metzger in 2011, he explored the evolution of the torus formed during the quasi-circular wide dwarf neutron stars merger. Results showed that the nuclear reaction are important compared to the viscous heating, and that the radiatively efficient nature of this disk should result in significant outflow. Recently, we have reported two-dimension time-dependent simulation of the disk, including a physical equation of state, Helmholtz, coupled 19 and 47 isotopes nuclear reaction network, viscous angular momentum transport, and self-gravity of the torus. And in Newton stars wide dwarf work, detonation are also reported. So I'm going to use the same, but with in some of our simulation, I don't need the nuclear reaction because the basic 19 or 13 isotope or the alpha chain in flash, they don't including the recombination between helium and hydrogen. So it's useless if we just trying to determine. But we also check this if there's any numerical effect, and it's not affect any of the result. So far, you can see here, it's a map of our quantities I decide to present in this work. Here, this is the evolution in time. Like, here you can see the time in viscous time and in seconds, and it's going like this is the density and temperature, the ratio of the radiation pressure to the total pressure, and here the total specific energy, the last one, and the pink contour. The pink contour you can see here is actually the separate the unbound ejecta from the spherical accreted envelope that remains gravitationally bound on the wide dwarf with specific energy below zero, negative. And I know just the difference in the radial scale between the columns with the final two snapshots showing the same epoch, but at different special scales. So you can see the second, actually, it's our summary. The secondary, it's not unbound in disk outflow, will end up as a spherical shell on the wide dwarf surface with an estimated mass, accreting mass between 10 to minus 3, 10 to minus few times 10 to minus 2 solar mass. As you can see here, as I mentioned, I have a nice model figures, but I think it's I don't have the time to present all this. So here you can see the cumulative mass with time accreted by the wide dwarf and the unbound ejecta mass as a function of time in units of the initial viscous time scale for the model where the wide dwarf is 0.6 and the main sequence is 0.3. The typical, actually the majority of the CV system believe this is the wide dwarf around 0.6. And the A2 model of the blue curve is like the other model with the wide dwarf with different main sequence mass, and the unbound ejecta calculated in two ways, actually, according to the positive energy in the solid line and the positive Bernoulli parameter, the dashed lines. The bound masses were the accreted into a pressure-supported envelope on the wide dwarf surface. We take that the angular velocity, it's below 0.2 of the Keplerian velocity, are shown as dashed line, and shows most of the original torus is ejected. Most it's close to 0.19. So the mass we start with 0.2. And the significant mass above 7 to minus 3 solar masses has accumulated into a quasi-spherical envelope around the wide dwarf. Here is the accretion or the mass loss from the system we get for all our model. Here you can see the ejecta mass as defined with a positive specific energy. You can see the the total mass accreted by the wide dwarf. We define as a gravitational bound material with negative velocity below 0.2 of the Keplerian, and that means it's the centrifugal supported. And the final outcome actually provides a second definition of the mass of unbound ejecta as a material with positive Bernoulli parameter. Although here the material where the positive specific energy is below zero and the Bernoulli parameter above zero is not unbound by the final snapshot of the simulation. It's in principle, it's high enough that it could become unbound by pressure forces at the later point, and the distinction makes a little difference between the ejecta mass defined by the positive specific energy to the Bernoulli below 10%. This is the difference between the Bernoulli calculation based on the Bernoulli calculation positive specific energy. Here you can see, here I present the evolution of the merger debris from the rotationally supported disk following the disruption to a pressure-supported envelope on the wide dwarf surface, of course, over several viscous time scale. You can see here. Here we just showing us like it's a different several snapshot from our A1 model where the wide dwarf is 0.6 and density is 0.3. So this is the fiducial model where the angel average radial profile of the unequal velocity. Here you can see in the bottom panel, and the upper panel is the CS, the sound speed velocity, divided by the Keplerian velocity, where the quantities shows the importance of the rotational and pressure support, with the remnant torus now separating large. You can see radii large, like above 10 to 11 centimeter, through a combination of viscosity and radial pressure, and the radial pressure forces. So this is what our conclusion from this nice process. So as I mentioned, we report in our previous simulation, there could be a nuclear burning is super important. So yes, nuclear burning will be important if the burning time scale at a given radius in the disk, the midplane, is shorter than the local viscous time scale, where the temperature can reach above 10 to 8, actually 2 times 10 to 8 Kelvin. And the nuclear burning could have a large dynamical effect on the disk evolution, as occurred in the merger of wide dwarf neutron star scenario. This is because the energy available through the hydrogen burning, well, it's 6.3 MeV per nucleon. This energy will only be released if the infalling metal has enough time to burn. So, and actually, if this energy from the hydrogen burning exceeds the gravitational binding energy, in this case, it's 0.1 MeV per nucleon, it could be enough time to burn all the hydrogen. So other work on luminous red novae shows resulting luminosity between 100 to 1,000 solar luminosity can reach this value comparable to the following of the CV system in our work from residual hydrogen burning on the wide dwarf surface, I mean. So the L shell, the luminosity of this shell we found, it must be above 10 to 1,000 solar luminosity. And our summary is one caveat, it's that the wide dwarf surface will undergo hydrogen shell burning, inflating the remnant into a giant star of luminosity between 300 to 5,000, and coming with effective temperature around 3,000 Kelvin, and lifetime between 1,000 to 10,000 years. And we take all this energy we have, and we calculate analytically the luminosity and develop one zone and multi-zone radiative transfer radiation luminosity time, and compared to what we know from the observation side.
Sorry, Yossef, sorry, yes. Sorry for the interruption. I think I'm now lost about the basic picture. So, okay, so your overall mass donor is donating mass at some relatively pedestrian rate of something like 10 to the -4, 10 to the -5, maybe even less solar masses per year, right? It's a pretty slow process, right? And then over 10 years or 100 years, I mean, we're talking about years or decades time scale. You're building up a disk, and the disk is just kind of sitting there, right? Your white dwarf is so the material is actually sitting in the disk for a long time, right? Until you
Yes.
build up a significant amount of material in the disk, maybe 10 to the minus 4 solar masses of material in the disk, right? And then you release that material over a very short time scale, which is a viscous time scale, right? Which is, you're saying is much shorter than the time scale in which you're building up the disk, right? So why do you only care about nuclear burning relative to the viscous time scale if the material is sitting in the disk for much longer? So I think there's something I'm missing here fundamentally.
Yeah, okay. So I say we can't follow in our simulation the nuclear burning because it's require the light reaction network that we don't have in Flash. I'm working on somebody from Santa Cruz trying to develop this together. So we're trying to estimate the nuclear time scale compared to the viscous time scale or the heating viscous. And what we found that we have, as I said, the hydrogen burning, it requires 6.3 MeV per nucleon, and we need the binding, the gravitational energy, it's not enough. So we think just to talk about the burning in the disk, it's not actually, it's irrelevant to what we're trying to say. That most of the shine or the outburst, it's come from the burning on the surface of the white dwarf. This is what I'm trying to say. Like, as you can see here in the disk, there's nothing happened, just standing. But the burning happened in the white dwarf surface. In a few time viscous time scale, like here, actually, around between 1 to 2 viscous time scale, there's happened the burning. After that, nothing happened. There's not enough energy or heating mechanism to burn much the hydrogen or the helium we have. So this is why we get this spherical shell in the white dwarf, and later on, like 10 to minus 3 years, as the CV system, there's still accreting mass, and they come again, they do the same cycling, and that's the again the burning, and we're trying to estimate the luminosity of these after like 4 to 10 viscous time scale. What happened? What is the mass, and what is the temperature surface on white dwarf, and what is the minimal energy we need to heat up again the surface of white dwarf to see the outburst of this novae or CV system. And this is what we did actually. We built up based on our hydrodynamic simulation. We developed the multi-zone shell burning analytically. Actually, it's not based on the simulation. Simulation just drive or motivate us to the after few viscous time scale, what is the final temperature and how big this shell, and what is the mass on the top of white dwarf, and then we develop our radiate or burning shell model. So this is what we did. It's not in the disk. In the disk there's nothing happened. There's no burning in the mid plane. It's different than I'm just try to describe how the same mechanism as white dwarf neutron star, but there's no exactly what as you say, there's no enough the viscous time scale to and nuclear burning. It's not it's not match, and there's not enough energy to trigger any flash or helium or hydrogen burning. So all what happened, it's happened on the surface, but this is what we see. Is it clear? I make it more.
Thank you.
So far, the optical light curve of the CV merger, assuming ejecta parameter derived by our simulation, it's around 0.3 to 0.2 to 0.4, with we developed the one-zone model for different values of ejecta velocity. Actually, this is also based on our simulation. We take the velocities here, as you can see, in different ejecta velocities, 400, 700, and 1,000 kilometers per second. And the solid line shows the more physical multi-zone characterized by the distribution of the ejecta velocities as motivated by the results of our numerical simulation. In orange here, you can see what happened if there's no hydrogen at all. It shows the light curve obtained if we assume adiabatic evolution. This is what most of the previous work assumed. There's no hydrogen reaction at all. So in our 1D or multi-zone model, we get this radius, this curve, the black one, and we including the energy released by hydrogen recombination in our multi-zone model. So far, we found the radiation released in the expanding disk ejecta energized by the hydrogen recombination on the wide-dwarf surface. Powers optical transit emission with a peak of luminosity between 10 to 38 and 10 to 39 erg per second, and characterized time scale of a couple of months. So far, it's not a complex or final view of this work. We completely trying to deep in. This is something we're trying to do now, including the interaction shock, as you can see. We know that a few studies they studied the shock power of this transient, because in the last decades or so, we have done a better job exploring the transient sky, and we have discovered many new classes of diverse transients. Many of these too luminous or evolve at the wrong rate to explain binuclear radioactive energy. But we can explain it in, as I mentioned, in significant energy in the shock interaction with efficient transform into radiation. And such event as the most luminous supernovae, for example, the fast blue optical transient, all these, or the super collapse, also all, of course, the collapse scenario, and the tidal disruption event have all been successful as being powered by the shock interaction. So why the CV system is not? In the recent studies, we found that the shock, the density of the shock, it is so dense in novae. Actually, these done by Laura and Brian and again, what the name of Elad Sternberg, I think. Yes, they published two papers recently about the shock in novae, and it's actually often difficult to prove that they are powered by the shock. So I'm trying to help with this simulation to understand more the shock, and including the late reaction network to see if there's the assumption about the recombination energy is realistic or not. So, so we take our results compared to the luminosities and the time scale of the prompted optical transient, as you can see here from the CV merger, and we found it's similar this classical novae and luminous with novae.
Yossef,
And
I know that we started
yes.
a bit late and you had some questions in the middle, but we do need to finish soon. So maybe take
okay, yeah,
at least 5 more minutes for the formal part and we can keep on discussing later.
Okay. So what I'm trying to say, we compare our calculation for the time and well, we look at the catalog, the galactic novae catalog, and took all the slow or the very slow novae with time to decline from the optical maximum by 2 magnitude T2 and above 100 days and the T3 above 150 days, and trying to find what is the component of this system. And we found here, you can see what it could be the donor for this system, and we find out of 22 of these, it's a slow classical novae known in our galaxy, and there are 4 cases where we cannot completely exclude the behavior expected for the following the CV system. So this is my summary, and I can take questions. Thank you.
Okay, yeah, I shouldn't have rushed to if I knew you had me on the slides. Sorry about that.
It's okay. No, I hope it's if it's something that clear, I can repeat it and trying to make it more clear. So anyone, any question?
Yeah, are there any questions? People, please raise your hands or just ask. All right, if not, then maybe we can clarify some things. I was wondering, I think going back to Ilya's, to what Ilya said about the disk. So I think, yes, the picture is a bit confusing because I think initially, oh, wait, there's a question from a student. I think it's more important. So he was, Alexander Kemp was, I was wondering if you compute nuclear yields.
Yes, we did what we already have, like 19 isotopes, but these 19 isotopes network or higher one, they don't include the recombination, specific recombination between the hydrogen recombination. So this is what we said. It's not so effective if we did it in the 2D in our flash simulation. And this is why we just estimate analytically what is the hydrogen recombination and where it's could occur in the surface of a wide dwarf, and calculate the luminosity peak. So we have it, but specific, it's not useful. It's useless because for this scenario we need just the hydrogen recombination, and I think it's not available specifically in any nuclear or thermonuclear code. I think Enrico Romero's and Santa Cruz and their student, they published something about the common envelope work for 1 year, and they include this. They have it. It's not public in Flash. So I connect with them, trying to include it. I hope just to check our results more honest.
Okay, thanks. So, I mean, in your last point, I can ask a question if nobody else wants. In your last point, you mentioned that there's a similarity between a CV merger and a stellar merger, and stellar merger, right? So I'm just wondering, yes. I mean, in the CV case, you have one of the objects is compact, so the other one just is disrupted and kind of has this accretion torus or whatever. But on the other hand, for stellar mergers, you may have some almost similar masses stars, So you won't really expect to have disruption. So I was wondering if you expect some qualitative differences in the modelings of stellar mergers compared to CVs.
In the stellar, okay, so specific here in our simulation, as I mentioned, we have a torus. In the stellar merger is, I think it's, most of the people think it's like as a spherical. So it's a different, but I can just say it's at the end. It's yes, the temperature and the primary surface, it will be different, so, like much less than in here what we did, because we really need to be so close, and accretion it's make it much hotter than just stellar evolution. This is what the stellar evolution simulation published in the 90s and beginning of the
Yeah, and I guess at least for stellar mergers, sorry, yeah. So if you have more spherical configuration, do you still use these alpha prescriptions for disks, or you have something more like a spherical modeling similar to like supernovae, ejecta, and interaction with the circumstellar medium, stuff like that?
I don't. No, we don't. We have just alpha viscosity, and we run one model just to make ourselves like relax with magnetic field. But we take the typical magnetic field, and it's take infinity time for this simulation. So this is why we stay with alpha viscosity, just the alpha viscosity with this disk. But for the stellar evolution, the stellar merger, I think you need, of course, with different assumption, because it's alpha viscosity. It's not something you can assume that.
All right. Any more last-minute questions? If not, I think we can finish our formal part. So let's thank Yossef, and I'm going to end the recording. So thank you for agreeing, giving a talk in this odd hour for you. So thanks again.